All right, this is lesson 8.8. I've decided to create a lesson for you rather than have you go through the Project STEM stuff. This is about sorting and searching. So, reminder of what an algorithm is. An algorithm is a set of steps to perform a task. We like to create functions for our algorithms. Now you're going to watch this short video about algorithms. All right. So that was a lot, but we are going to be talking about functions to create our algorithms for sorting and searching. So let's talk about this guessing game. And have to exit full screen. Our guessing game. You have the numbers 1 to 15. One of them is the correct answer. Each time the computer will tell me whether my guess was too high or too low. So I could say, all right, well, let me guess 1. All right, it's higher, so I guess higher 2. Nope, it's higher 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh my goodness, it took me 14 guesses to get there. Now I might get lucky. The number could have been 1, but that gets to be a lot if I have more and more numbers. A better method that you may have thought of right away is, okay, well, it'll tell me if I'm too high or too low, so let's pick something right in the middle. I know that nothing on the rate of 8 is correct now, so let's pick something in the middle, 4. Okay, it's higher than 4. Pick something in the middle. 6 was the number. There we go. It was much faster than guessing every single number until I got there. So, there we go. Algorithms in your life. What algorithms do you use in everyday life? Because we all use algorithms, whether we think of it or not. And do you think you could write a program to make them more efficient? Also, what algorithms do you think are used by your favorite games and apps? Give me a few examples. So this section's about searching versus sorting. Searching is finding information in our list. I want to know, does the element milk appear on my grocery list? Sorting is reordering it to make it easier to work with. Maybe I want to sort my grocery list based on where it is in the grocery store. We can write algorithms for both of these. So there's 2 different types of searches. A linear search checks each item in a row from the first to the last. That's the kind of search I did right away in my guessing game. Then there's a binary search. If your list is in order, the binary search is much faster. You check your center item. If that value is too large, check the center value of the first half of your list. If the value is too small, check the center value of the second half of the list and repeat over and over. That's what I did the second time through the guessing game. I guessed 8 first. It told me whether that was too big or too small. Then I only had half the data to work with. I guessed the middle of that one. It cut it down by half again. You can see that that's much faster. So binary search in a guessing game. We are going to pick a number between 1 and 100. I'm telling you the number is 87. But if I wrote, if I started guessing and I started at 1, it would take me 87 guesses to get all the way up to 87. Instead, if I guessed 50, okay, that's too low. Then I'll guess 75. That's too low. Then I'd guess right in between 75 and 100, 87. Look at that. I got it in 3 guesses instead of 87 guesses. So we're going to chat about how to write that code. So over here, I have import random. I have a list of values that's empty. And I used a for loop to create the list of values 1 through 100. And you can see that if I just print my list, and we'll get rid of this stuff for now. I get the values 1 to 100. All right, I'm going to have the computer generate a random value, 1 to 100. All right, it's going to pick something. I have no idea what that is. I'm going to start with a guess. Now, my guess, I would say I want to start with 50, right? But I would actually do this a little differently. I would create a minimum, which is going to be 1 because that's my smallest number, and a maximum, which is 100 because it's my biggest number. My guess is going to be my maximum minus my minimum divided by 2. Because I wanted to check the middle. Then, while my guess is not equal to the value, I want to check a new one. But if my guess is too small, my guess is smaller than the value, I want to check numbers that are bigger. So I'm going to take my minimum value and reassign it to whatever that guess was. Otherwise, if my guess was too big, it's bigger than my value, I want to change my maximum to whatever I just guessed. Based on whether my guess was too big or too small, it becomes the new maximum or minimum. Then I recalculate what the guess is. It's max minus min divided by 2. And it'll run again. And let's also count how many times this takes. So count equals 0. If I run my loop, I want to add 1 to my count. And then we'll print the number is value plus it took our count guesses. Let's run. All right, you may notice that my code didn't run anything. That's because I made my guess incorrect. First of all, I shouldn't take max minus min divided by 2. It should be max plus min divided by 2. That's how you find the average of two numbers. Second of all, this could give me a decimal. And if I'm doing a random integer, I never want a decimal, so I need to turn that into an int. Both times that I make a guess. Now let's run it. Look at that. The number was 28. It took us 7 guesses. The number 22 took only 4 guesses. 81 took 3 guesses. So I could keep doing that, but this function will tell me how many guesses it takes to guess whatever random number it was. All right. So we wrote that code. And now we're going to look at another code. We're going to see if 67 is in a list of prime numbers. So I have already taken my code. Notice I'm on the same one. And I added my list of prime numbers. I want to know, is 67 prime? Basically, I want to search my list of prime numbers to see if 67 is in it. So I'm going to say, I'm going to write a loop to search through all the elements of my list. We've done that several times. That is for I in range, the length of my list, which is primes. And then I want to take my primes I. That'll tell me the first thing, second, third, fourth, blah, 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 blah. And I want to find out if that's equal to 67. So if primes I double equals 67, then I'll print 67 is prime. Otherwise, we'll print 67 is not prime. Let's try that. Uh-oh. It tells me 67 is not prime several times because I told it to. My first element, it checks, it's 2. 2 is not equal to 67, so it says 67 is not prime. Well, that's not really what I wanted it to do. I just wanted it to say, all right, if I get 67, 67 is prime. There we go. What if I tried a different number? What if I tried 30? Obviously, I would change this to 30. Oh, it didn't print anything. So the question here is, how do I ask my computer or my program to tell me, well, that one is not prime? instead of printing it all those different times. For this case, I would recommend making it a function. So I have my list of primes. I'm going to def is prime. It's going to take our list and a value as parameters. So for I in range, the length of my list, if my list I double equals my value, we will return our value string value plus is prime. Oh no. And if it's not, we'll run the loop again. Once we come out of the loop, if it hasn't been primed, we will return not prime. Now, instead of having my for loop down here, I'm just going to call my function. I'm going to say print is prime primes. Comma, what value I want to check? I want to check 30. Not prime. Let's say I want to check 79. 79 is prime. Now I can search for anything I want by creating a function that returns things. Returning, remember, ends my loops. So as soon as I return one thing, it doesn't return anything else, which is why this not prime only shows up if it wasn't prime. So if the item is not in the list, none should be returned usually. And that's a way, separate way. If I take my primes dot index of 30, I print that. I get 79 is prime, 30 is not in the list. 30 was not prime. So the dot index method will tell us the index of the first time that item occurs. So if I put dot index of 3, it'll tell me 1. Boom. Instead, if I want to count the number of times that occurs, well, 3 would give me 1. If I put 30 in there, now that's going to give me a 0 because it's not in the list. All right, so running time is also important. For binary search, the running time will be log base 2 of the length of the list. A linear search is just the length. This is the number of guesses it'll need at most, not the actual time, because each guess is performed super, super quickly. But more guesses equals more running time. This log, what it means is 2 to what power would give you the length of our list. So if my list has 4 items, 2 squared gives me the length. It would take me 2 guesses to get the answer. If my list has 16 items, 2 to the 4th power gives you 16. It would at most take us 4 guesses in a binary search. That's all that means. Just understand that a binary search is much, much faster than a linear search the majority of the time. And then we have this. These are some cards, and we're going to look right here. So you'll implement a sorting algorithm. I want to put these in order, smallest to biggest. Now, there's several ways I can do this. I could say, all right, well, 5 and 13, 13's bigger, cool. 47's bigger, good. Oh, 17's not bigger, so I'll swap it there. 53, 2 has to go all the way back down here. Keep moving it till it's where it should be. All right, 7, I'll move that one also. Move it there. 29, okay. There it goes, 41. So it's every element I encounter, I move to where it should go. And then 23. There we go. I got it. Or I could say, all right, well, what's the smallest card? That's the 2. Let's put it first. And then the 5, let's put it second. The 7, put it third. 11. Then move the 13. Then I got a 17, 23, 29's already there, and swap those 2. Notice how much faster that was. That's what we want to kind of think about in our sorting algorithms. So lessons 8, 9, and 8, 10 will walk you through creating those search and sort algorithms. Watch those carefully, use what they say. Best of luck.